To start building a simple PID controller model, first double-click anywhere on the screen, start typing step in the search bar, and select the step block. A step block is used to generate a step input signal, which changes from one value to another at a specified time, making it ideal for testing control systems. Next, double-click on the screen, type transfer function in the search bar, and select the transfer function block. The default block represents a first-order transfer function, but you can modify its parameters to make it a second-order or any other order transfer function. A transfer function is used to represent the mathematical relationship between the input and output of a system, making it essential for modeling and analyzing system dynamics. After that, search for and add a gain block. Connect it to the model. A gain block is used to scale the input signal by a specified constant factor, adjusting the magnitude of the signal before it is processed by other components in the system. Then add a scope block in the same way and link it to observe the system's response. Next, move to the scope block. You'll see a plus sign. Click on it to add another input to the scope. Then, connect this new input to the input step block. This will allow you to visualize both the input and output waveforms on the same scope. Now, run the model and observe the results. The blue signal represents the input step function, while the yellow waveform shows the output after passing through the transfer function. The transfer function processes the input, modeling the system's dynamic response, and alters the signal based on the system's behavior. Next, add the add block to the model. Connect one input of the add block to the step block and the other input to the output line. Then, link the output of the add block to the transfer function. This block is used to combine or manipulate input signals by performing mathematical operations like addition or subtraction, making it essential for integrating different components in the system. Afterward, reconnect the scope block to the step block and run the model to observe the changes in the system's behavior. Click on the add block and change its second operation to subtraction. Additionally, you can change the shape of the add block to adjust its functionality. After switching it to subtraction, run the model again to observe how the system reacts to the updated configuration. Now you can modify various values and observe their effect on the model. For example, I'm adjusting the gain value and experimenting with the model. You can also tweak the parameters of the step block and see how it influences the model. However, since we don't have a controller in place yet, these changes won't alter the shape or behavior of the graph. So, I'm resetting the step block parameters back to their previous values. The issue with this model is that it currently lacks a controller. To address this, we need to add a PID controller. A controller is a critical component in a control system that adjusts the system's input to achieve the desired output by minimizing the difference between the actual output and the target. Search for and select the PID controller block to include it in the model. If you click on the gain block and hold Shift while dragging, it will disconnect from the model. This method can be used to remove any block from the model. Connect the PID controller to the model as illustrated. Run the model and observe the effect of the PID controller. The PID controller adjusts the system's output by continuously calculating the error between the desired setpoint and the actual output. Now, modify the transfer function to different degrees to observe how the PID controller responds to each variation. Now, modify the transfer function to different degrees to observe how the PID controller responds to each variation. A transfer function represents the dynamic relationship between the input and output of a system. It can be adjusted to model systems with different characteristics, such as first-order or second-order dynamics. When using a PID controller, the transfer function helps determine how the controller interacts with the system. By changing the degree of the transfer function, for example, from first order to second order, you can observe how the controller adapts its response to different system behaviors, such as damping, overshoot, or settling time. This allows you to fine-tune the PID parameters for optimal control performance. Experiment with different values and observe how the system behavior changes. Take the time to explore and research the underlying principles of the system's behavior from various sources. This will help you understand the reasons behind the changes you see in the model. By learning more about the system's dynamics, such as how the PID controller interacts with different transfer functions, or how parameters like gain, damping, and time constants affect the response, you'll be able to interpret the model more effectively. Understanding these concepts will allow you to make informed adjustments and better analyze the performance of your control system. Open the PID controller block and examine its parameters. These parameters, proportional, P, integral, I, and derivative, D, can be adjusted to influence the system's behavior. This is a basic PID model that anyone can create, but it's important to study the underlying concepts in greater depth.